Welcome to another vibration research webinar. My name is Brad and I'm with VR Support over here. So if you've ever reached out to us with any questions, software or setup related, it's possible that we've had some interaction in the past. But as always, if you do have any questions, always more than happy to help with anything vibration testing related. So one of the questions that has come up in the past for us in support is, there's a lot of different ways to run vibration testing, but sine and random are actually, going to be some of the more common testing methods. And, what's going to be the better test, right? So that's the question that we're aiming to answer for this webinar today. So just to get started, we'll go through vibration research core values. So our focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Our core values are collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. So our goal is, for these core values to really shine through in our products and in the software and in our service, really, at a personal level and at a company level. So it's something that we really keep in mind in all aspects of the business. Now, to get to the question, which test should I run? So, I have a sine test or I have a random test. Is it possible to pick one over the other, or which one of these tests is going to be more damaging, or which is the appropriate test to run? What levels do each profile or test, how do I compare them, basically, is the question here. So we came up with a method to compare the results or compare the expectations for each of these tests and kind of drew some conclusions from that. So that's what we're going to talk about. So here's the two tests that we put together. So on the sine test here, I have it set up at 3.5 Gs from 5 Hertz to 50 Hertz, and then 1.5 Gs from 50 Hertz to 300 Hertz. On 0.4 inches peak to peak displacement. And then for the random test, you have a flat random spectrum from 10 Hertz to 40 Hertz here, and then a slope down from 40 to 500 Hertz. Again, all axes are tested at the same level. So these are the two tests that we're going to use as our basis. And what we're going to do is figure out the best method to compare these. And the best method, or easiest method in this case, is similar. G peak and understanding the peak acceleration being generated by each profile is one simple method to compare random Gaussian test to a sine test. What we're going to cover in the next couple slides is how that math is done and some conclusions that can be drawn through that comparison. So I'll just go next slide here. So we already know that sine vibration is measured in G peak. That's how we define our test profiles. For random vibration, on the other hand, it's defined in power spectral density. So G squared per Hertz over a particular frequency range, and is simplified by looking at G's RMS. So with the G RMS measurement, it's possible to approximate the G peak or the peak accelerations expected for a particular GRMS test. If it's Gaussian vibration, we can assume that there will be 4 sigma peaks, or the peak acceleration will be 4 times greater than the G's RMS. So that simple multiplication can be done. G peak is approximately 4 times the G RMS of the test profile. So if I look at the G's RMS of this particular test profile, it comes out, says we have the approximate G peak for this test will be 4.3 G peaks. In my sine test, I have 3.5 G peaks across. In my random test, I can see up to 4.3 G peaks. So does that make the random test more damaging? That's the question that we're here to answer. So before we can complete an analysis and really get into this, we need to look at a couple assumptions that we make for these tests. So the first being that failure in a product being tested is caused by peak G levels experienced by the product. So really getting into, what is the G level being excited by a resonance. So this peak acceleration are what's causing damage to a product if they're exciting resonances. What's typically that's typically going to be where a product is damaged when it's being exposed to a resonance. So if those peak accelerations are exciting a resonance, it's causing damage. Most products have resonances at multiple frequencies, so that's going to be pretty common for most parts or products that are undergoing vibration testing. In sine, the resonances are excited one at a time. So as your sine sweep passes through that resonance, it excites the resonance and it falls off and then goes to the next one. In random, those resonances are all going to be excited simultaneously. Then finally, when a resonance is excited, that response is amplified by the Q factor or quality factor of that resonance. And the amplification of that acceleration is the primary source of damage to a product while under test. So sine is really simple. We're trying to figure out the amplitude that a particular resonance will experience when a vibration or when acceleration is input to it. So if you know the Q, it's very simple to calculate. If I look at my control input, in this case 1G, and I'm looking at the 139 hertz resonance right on top here, all I have to do is multiply the Q of that particular resonance by 1, my input acceleration, and I'll get the calculated response of my product. So in this case, I input 1G and the Q of 9.8, I should see approximately 9.8 Gs. In this case, I'm seeing about 8.39. So this could be because of the difference. Maybe there's a difference because my accelerometer is saturating. Probably not in this case, just because we're only testing out, we're only seeing about 9 Gs acceleration in this case. So more likely has something to do with the sweep rate, perhaps sweeping too fast through the resonance during this test. And so then I didn't appropriately excite that resonance to see the total peak where we would expect to at 9.8. But then for the random, so a little bit different here because obviously this is random. So not all vibration being applied is amplified by a resonance because that energy is being applied across the wide frequency range, not specifically where each resonance is in that frequency band. So if the Q of that resonance is greater than 5, it acts as a bandpass filter with amplification equal to Q and the bandwidth equal to the half power bandwidth. That's very similar to what we saw in sine. So if the Q is greater than 5, the resonance acts as a bandpass filter, meaning that if I put 1G peak in that resonance, if I have a Q of 10, I'm going to get 10 Gs out so long as the Q is greater than 5. So in most cases, we're going to assume that the Q is greater than 5. For a given RMS level, the PSD is inversely proportional to the full bandwidth of the random section. What that means is if I have a 2 GRMS test from 100 hertz to 500 hertz, the G squared per hertz measurement at each frequency is going to be higher than if I have a 2 GRMS test going from 10 hertz to 5,000 hertz. So smaller frequency range, in order to get the same G's RMS, is going to have a higher G squared per hertz measurement at each frequency. Knowing the Q factor and how the product responds to a particular input, we can begin some of those calculations necessary to kind of evaluate these tests. So continue to the next slide. This is part of the formula that we're going to be using to do that evaluation. So random tests, as we all know, are defined in terms of PSD, the power spectral density, which is an amplitude squared measurement. In order to use the Q, we'll have to remember to use the Q squared in this case. So as discussed in the last slide, and we determined that any resonance with a Q greater than 5 acts as a bandpass filter. So we need to calculate the energy that is amplified by the resonance, not the energy that is applied across the entire frequency range of the test profile. So we need to target each individual resonance. We can use some substitution in the math to create a calculation that will tell us the expected G peak acceleration. So if I'm using a quality factor and I'm using the delta F to look at a particular resonance, I can convert it to the formula all the way down at the bottom here, where I'm taking my PSD times the quality factor times delta F here. So, and that's going to approximate the peak acceleration being seen for that random waveform in order to do that comparison at the end. So just a couple notes here to include. Peak acceleration is proportional to the square root of Q. A high Q resonance will result in a more severe sine test if all the parameters are equal. In addition, a Q is also proportional to the square root of the resonant frequency. The higher the resonant frequency, the higher the peak acceleration response. So this gives us a chart to compare the change in quality factors. So what we did is, based on those test specifications from the beginning that we looked at, we generated a peak acceleration graph that shows the resultant G versus frequency of the sine and the random tests based on changes in the Q factor. So you can see that in the graph here to the right. Now we're just going to go through some of the setup for our real world proof of this sine versus random comparison. So we kind of have this theory, some rough math, but in order to prove it, we're going to show how it works and run the test in the lab. So we have a metal rod with an aluminum mass mounted at the top, and then we put accelerometers at the top of it and ran these profiles so the masses are mounted on a slip table. And then this is what you end up with here. So on the left, the sine test, obviously, and then on the right, you see the random test. So we observed two major resonances below 300 hertz here. In order to properly compare those resonances, we need to convert the results from the random test from G squared per hertz into a G peak value using the calculations from our theoretical example. So these are the results from the live test that we ran in the software. What we did is record the waveform for each so that we could post-process it later on. And then we were able to analyze the time history file with higher lines of resolution. We actually determined that the quality factor of the first resonance at 27 hertz would actually be closer to 140. And then the quality factor of the second resonance would actually be closer to 200. So when using random, more lines of resolution will help help you better negotiate or target a particular resonant point. If you have too few lines of resolution, then you're not going to see what the actual peak acceleration being brought into the resonance is. If you have the minimum recommended by mil standard is 3 lines within the half power bandwidth, but more lines is not necessarily a problem in this case. So there are other issues that can arise with using extremely high lines of resolution, but if you're simply looking to pick out resonances and figure out exactly where they are, the other method you could use is recording that waveform at a higher sample rate and then post-processing with higher lines of resolution. So that way you can more accurately determine exactly where those resonances are. So that said, I have calculations down here for the 27 hertz bin. I have 0.015 squared per hertz. My Q was 140, and then resonance was at 27 hertz. So to do the math, I get approximately 30 G peaks calculated. If I look at the actual waveform, I can measure, we got right around 28 G peaks you can see in this waveform. So if you need to take a closer look too, I think we'll make these slides available too. But for the second element, we have a Q of 200, resonant frequency of 62 hertz, and a PSD or G squared per hertz for that frequency band. It was 0.00673 times 37 Gs, and then the actual peak acceleration was 40 Gs. So next slide. Now we can look at the comparison here. So I have at the control point 3.5 Gs coming from the Sine test at resonance, random 1.05 Gs RMS. My random peak acceleration measured on the control point was 4.8 G peaks, and my predicted G peaks was 4.2. So now if we look at resonances, you'll start noticing something a little bit odd here. One, the Sine acceleration doesn't seem to be high enough. If I put in 3.5 G peaks to a Q of 140, I should see much higher acceleration than 42. 3.5 times 140, I should see, roughly 490 G peaks. And then with the same calculation, 700 G peaks for the 62 hertz resonance. So something that we might be missing here in post-process, we noticed for the 27 hertz resonance, the Sine sweep passed too quickly through that lower frequency. In order to properly excite the resonance, we could redo the test with a slower sweep rate and really try to focus on that resonance a little bit more, or use a resonance track and dwell feature to excite that resonance, and would result in a much higher acceleration closer to that 490 range that we expected. For the 62 hertz resonance, it's likely that we were using a 50 millivolt per G accelerometer. That those at that sensitivity, it's going to be saturated at 100 Gs. So because the problem we noticed in the recording is that the accelerometer was saturated. So if we used something like a 10 millivolt per G accel, we could measure out towards 500 Gs and actually reach the appropriate acceleration for this test. So the random peak values are pretty close to what we expected. They're not going to be exact, but just simply because of the randomness of our waveform. Then the 27 hertz resonance, you have 28 G peaks measured, 30 G peaks calculated. For 62 hertz, for the 62 hertz resonance, we have 42 G peaks and 37 G peaks calculated. So at the control point, the random test has higher peak acceleration than the Sine test. And then at the resonance at the resonant points, the sine test has higher peak acceleration than the random test. So if we go back to our assumptions from the beginning of the presentation, we can say that from the product's response, the sine test is actually going to be more damaging than the random test, given that we're testing in the same conditions. So we can, basically what we can learn, the relative severity of a test varies depending on a product's resonances and the quality factor. So that comes from the graph that we saw for the change in Q earlier, and how the sine test was pretty flat all the way across, but the peak acceleration caused or expected in the random test varied. In general, when sine and random tests have a similar or the same peak vibration levels to the control, the product is going to see higher vibrations with the sine test than with the random test, just due to the resonances of the product. This is because all that energy and all that peak acceleration is being applied into the resonance as it reaches its peak and out of the resonance. So you're bringing up that resonance with more vibration, and it's being applied more directly to that resonance. Now when we look at the sine test, we're exciting a single resonance at a time. So if any of our resonances happen to excite or have an effect on other resonances in the product, when you use a random test, you can excite multiple resonances simultaneously. So that's kind of how they're different. You can find the problems that come from interaction or the effect caused by multiple resonances sort of fighting each other or helping each amplify themselves in a random test. So with that being said, would be the end of our webinar for today. I know this is kind of a shorter webinar, but if you do have any questions about the sine or random test that we set up and the methodology that we went through, always more than happy to answer questions related to the presentation. You can reach us at VR sales or support at vibrationresearch.com. And yeah, we hope you enjoyed the webinar and have a good one. Thanks.